Thanks for the opportunity. My name is Aravind. I'm the Chief Strategy Officer of Q-CTRL. I'm actually filling in for our principal scientist in our quantum sensing team, Russ Anderson, who couldn't make it here because of some travel issues. So, and my topic is going to be around quantum assured navigation, and specifically how quantum enabled PNT is helping one of our investors, and as well as technology partners, Airbus, navigate unreliable GPS. And I'll give you a broad overview of what we're doing in this sector, and then dive in. Can we swap the presentation now? Yep. Yeah, thanks. Okay, very good. So Q-CTRL's mission is really in making quantum technology useful. And those of you who are familiar with us, we do this on two different areas in quantum. One is in quantum computing, where we are extremely well known, and then quantum sensing, which is the other part. And in quantum computing, our infrastructure software provides performance management to drive quantum computing hardware to its absolute performance limits. And in quantum sensing, we provide a software ruggedized technology, and we have been known so far to work with defense agencies across the world, as well as primes, as well as SMEs focused on mission critical programs. So this talk is going to focus on quantum sensing. Specifically, we have developed in-house full stack quantum assured navigation solutions. And these rely on the properties of atoms. And in an approach that somewhat differs from the approach that others have followed, we did build our own sensors. And these include acceleration, 3-axis mobile strap-down accelerometers, gravimeters that use very, very low power, as well as fairly tight swap magnetic fields. And we make this happen using the exquisite power of the sensitivity of neutral atoms. And the reason we did this, rather than, I know this viewpoint differs somewhat from the earlier panel, rather than just use off-the-shelf sensors, is that we found that once you take those sensors out in the real field and you start playing with them, they are not as reliable as we want. I myself have a history in automotive, worked in several production programs, and I know what it takes to take very, very early stage sensors onto production level quality. And so while it does make sense to work on the right technology and bring it up to a certain level before you start to ruggedize it, and that's exactly where we are. But the real power of the real unique thing that we have done in this industry that others have not necessarily followed is the software ruggedization that we have using the unique quantum control capability that we have in-house. And those fall across two categories. One is in the runtime itself, using robust control, multi-feed forward control, etc. The other is in signal processing, and specifically denoising, data processing, and other similar capabilities of the stack. What we have done is optimize every layer, starting from the sensor to the highest level that gives you the best possible signal that makes mission critical applications happen. So because this talk is really about PNT, I'm going to focus on that one application, which is position navigation and timing. Modern aviation, I think GPS has been largely a boon for us. We use GPS for everything, but GPS is also vulnerable, and if it is a lights out sort of situation, the estimate is it's going to cost the US about $1 billion a day. IATA produces these maps of GPS denied zones across the world, and they're honestly everywhere, and I'll show you some data soon. And the data that I show on the top right of the slide is really on the border of Turkey, Syria, and Iraq, of GPS denied zones, taken from a recent snapshot. And but from a commercial airline perspective, really GPS unavailability is route limiting. What that really means is yes, there are backup sensors to GPS but there are various complications that get involved, and all of them through a series of steps, through a cascading series of steps, eventually result in operational inefficiencies. And that is what we're trying to avoid. And I have to say that, if you look at the people who make the aircraft, they've taken a number of steps to make sure that the safety is, the safety levels are maintained to the best possible extent with multiple redundancies, multiple different types of sensors. But at some point of time, there is a point where you do need a reliable backup to a GPS, and that's the problem that we are addressing that is of interest to airlines. Yeah, I mean the final deployed solution still has to exist, still has to manifest in the field, but this is what people like Airbus are interested in. Now, this is not a theoretical problem. There's cheap equipment out there for a few $100s. You can go and buy jammers, right? And these jammers exist in various sizes. And I show one such example. This is the Russian Pol-21 military grade jammer, and you're talking about jamming tens of kilometers at once, and this has caused big problems. And this is actually manifesting in the GPS denial incidents have really picked up. And if you look at what has happened just within the last 1 year, it's actually been crazy. So for obvious reasons, where GPS denial is happening most is really in the Middle East. But if you look across other areas of the world, the Black Sea, Russia, Korea, and also the India-Pakistan border, there are multiple disrupted flights per day, right? This is not to say, I'm going to be very, very careful to say this is not resulting in crashes today yet, right? That's not what it is, but we are simply recording the number of GPS denial incidents here. And at some level, these things cause stress and distraction and reduce crew confidence, right? So we internally conducted a survey across multiple commercial airline pilots, and the concern is high because these crew are the ones who have to respond to these issues when they come up, and when they do so, they're not able to do other things, right? That would that are in the normal course of their duties. They can't focus on. But the thing is, again, I want to be very, very cautious and not say that this is catastrophic today, but it is an area of concern, and this is being looked at. Yeah. A recent another extreme example was this whole Finnair thing this incident. There's a city in Estonia where only Finnair flies as an international airline, and because of GPS denial incidents, they essentially canceled all flights for a month until they could figure out an alternative solution. And you guys can look this up online. So now having set up the problem, let us look at the solution. So this is what is called as quantum magnetic navigation. And if you remember the times when you guys went hiking or in your scouts, how you used your map and compass, right? So map and compass is similar to this technology in that there's no GPS, right? So you're relying on the topographic features of the Earth to understand where the indentations lie, where the squiggles lie, and then using those features on the Earth, you're using a map and compass to figure out where you are and orient yourself. Now, the way quantum assured magnetic map matching works is using a similar technique, and the problem statement is we are looking to bound the positioning error, right? So it turns out that you need three capabilities. One is geomagnetic maps that are publicly available, and I'm going to double click on that for in a bit. The second is you need a really reliable quantum magnetometer. And yes, as someone who came from the sensing world, from a different automotive sensors world, I worked for two LiDAR companies. It's very, very tempting for me to go pick up a sensor off the shelf and see if it works, right? And the question is, are they going to work reliably, right? And there are some unique problems that crop up out in the field. And the third is the whole map matching piece of it. And it's not just map matching. There's several things that need to happen, including sensor fusion. And what that results is in a magnetic navigation corrected position, right? That's the fix that you eventually get. So various experiments have shown if you go back, optically pumped magnetometers, the information about them was published 10 years ago, and that's sort of when the sensors started becoming available. That does not mean that they were ready for real world applications, right? So since then, significant advances have happened, and we have been one of the companies at the forefront of it. And so what we're doing is using the Earth's magnetic fingerprint to provide the actual positioning rather than just the heading. Yeah, and because quantum sensors use quantum mechanical effects, they're not subject to the same kind of stress, F equals minus kx type of effects, and they don't suffer from drift that classical sensors do. And because of that, we are able to provide the necessary sensitivity as well as stability. And it turns out that quantum anomaly data sets are widely available. They're publicly available. But if you want a higher level, higher resolution for certain areas, that can also be arranged for commercial aviation routes. And they're available for various altitudes, and they're actually quite feasible even at airline speeds for navigation. Yeah. So now what happens when you take one of these and stick them in an aircraft, right? This is the type of signal that you get. So what you see as in red is the geomagnetic reference. This is the actual field that is coming from the Earth. But the problem is inside an aircraft, the platform noise generated by the aircraft itself overwhelms the whole signal, right? And that makes the navigation really, really hard. And it turns out that that using certain techniques, you can suppress the noise caused by platform noise, and to a point where you can completely recover the signal and perform magnetic navigation. And if you guys want details, please come and see me offline. I don't have a lot of time here to discuss this. And this has also been found through our simulations to be quite feasible for at altitudes and provide the necessary sensitivity for commercial aviation to potentially be feasible. Yeah, there's still a lot of experimentation to be done, but it is feasible. The necessary innovation that we brought to this field is this novel physics-based denoising approach, right? So there are various denoising approaches that are available. This is not just about taking a data set and throwing either a well-known filter that has existed for years, or even machine learning-based neural network type approaches, because they work up to a certain level, but beyond that you do need accurate physics-based modeling, and that hybrid physics-based modeling is the necessary innovation that we brought to this field. So if you just took a raw INS, inertial navigation system, and did not necessarily correct it, the positional error just increases indefinitely, as you can see in the green line. The best ML-based techniques based on open data sets, this is based on published information, can bound the error somewhat, right? But using our physics-based approach, we can reduce the RMS noise to typically, less than a third of what the best ML-based techniques can achieve, and that's the purple line at the bottom of the chart. This is not the only advantage that we bring. The real advantage is the learning time is extremely low. From a cold start, we are able to go on an aircraft and have the model learn typically in 15 to 30 minutes. There is zero calibration, right? So we don't need to recalibrate for different flight paths. We don't have to recalibrate for different latitudes. We don't have to recalibrate for different altitudes, or even different training maneuvers, right? This thing is extremely resilient. It's not brittle as you might otherwise cause it. So, we are a very real company. As an experiment, we did a ground-based trial. We basically took this magnetometer solution, strapped it down, put it inside a car, and drove it around, right? One of our ground trials that we conducted was at an airport, And what we did was follow the yellow line. Next time you are on a runway, you can see how planes follow the so-called yellow line when they're taxiing. So we did a taxi trajectory, and we closed the loop multiple times. And the repeatability of our technique is what you see. What you see on the graph on the right is actually 2 loops that we did, and you can see it's excellent repeatability. The only deviation is caused when there were other vehicles that came very, very close to us that disrupted the magnetic field. So it turns out that, look, the magnetic variation is quite heavy when you are close to the ground, and obviously the level of the signal change reduces significantly when you're up in the air. But this excellent repeatability proves that we can work either on the ground or in the air. And then we did one more where we closed a loop, and this is the world's, well, I think this is technically the world's first magnetic navigation demonstration. In a conventional van, we closed, I think it was a 14-kilometer loop or so. I have to go back and check. But essentially, we went on a vehicle, and essentially we did an entire loop, and we found excellent repeatability. And yeah, so it's really what you see in the gray line is the signal from the raw INS. So if you were to rely on unaided INS, essentially your bounding error would have kept increasing. But you see where somewhere in the middle our signal kicked in, and we were able to reduce the error to typically under 100 meters. So we have also packaged up some of the capabilities that we've built in a navigation capability simulator. And this is really great if you want a digital twin type model where you can do multi-mode, where you can have both magnetic navigation as well as gravitational navigation, which I did not cover. If you want to benchmark our performance as well as optimize routes and design different types of modalities. The sensor that you see on the right side is what we did for a partner who is designing submarines, for example. And there the sensor is a little big because, as Luca explained earlier, sometimes the sensitivity grows as the sensor size grows. And yeah, in that situation as well, the level of signal correction that we have is some of the best in the industry. Okay, great. So to summarize, right? So we have delivered software ruggedized quantum PNT solutions, and with a focus on industrialization, with a focus on production. And I covered the first 2 applications on the left side, but what we also have is this dual gravimeter that I just explained on the last slide, where having our software is the difference between your application not working and your application working. And finally, also we have field tested mobile 3-axis accelerometer so that you can dead reckon in a way that is more reliable than what is current. And yeah, so we are working with our partners, including Airbus, to enable a safe, efficient, and resilient aviation future. Thanks for the opportunity. And one last thing, we have a booth down in G5, so we would love to have you guys come to us and ask questions.